In this video, we're going to be talking about osmosis. Osmosis is a process in which phenomena flow through a semi-permeable membrane, which means only permeable or only certain things can go through that membrane, to equalize solute concentrations on both sides of the membrane. Now, this is something that you should have heard about a lot in biology because most biological systems use osmosis in order for water transport across cell membranes. Again, here's the video with the link at the bottom so that if you want to go back and play it again or you can't hear the audio on it, you can do that. I've already set it up to play here.
Hi, it's Mr. Anderson, and today I'm going to show you a quick little osmosis demo that I set up in my classroom. But before I do that, I should probably talk a little bit about what osmosis is. And so osmosis is simply diffusion, or the movement of water from an area of high water concentration to low water concentration across a semi-permeable membrane. So what does that mean? Well, if you look right here in this U-tube, that's what this is called, this would be a semi-permeable membrane. And what that means is it only allows a few things to move through. And so you can see right here that the water molecules are small enough that they can pass through, but the solute molecules aren't. Solute molecules could be sugar, could be ions, but essentially you can't make it through. They're too big. And so in relation to this side, the left side here we would call the hypertonic side. What hypertonic means is greater levels of solutes. And that means over on here, this in relation is going to be called the hypotonic solution. In other words, there's greater solute concentration on this side than there is over here. And so these are in relation to each other. And so what does that really mean? Well, if we were to zoom in at the molecular level, all of the water molecules are going to actually stick to this solute. So the water molecules are going to grab onto that. And since the water molecules are grabbing onto the solutes, there's not going to be a lot of water on this side. And so we're going to say that the hypertonic side is actually going to be an area where there's low water concentration. So over here, there's less solute, so there's less water molecules grabbing onto the solutes, and so the water is going to flow in that direction. And so however you want to think about it, is the water flowing from an area of high water concentration to low, or is the water flowing towards a hypertonic area? Either of those, it doesn't matter as long as you know which way the water is going to flow. And so what's going to happen to the water? Well, the water is eventually going to flow over to the side until the concentration of water on either side of that semi-permeable membrane is exactly the same. At this point, we would say on either side it is now isotonic, if I can spell that right. Isotonic means that water is still flowing back and forth, but it's flowing back at an equal rate. Now, if you were to think about this, if you were to watch this, it would seem somewhat magical as the water is just moving up on this side, just kind of against gravity and dropping on this side because you can't see the solutes, and so that's pretty cool. So let me show you the setup that I did in class in this osmosis demo. Find a good color. Right here I have dialysis tubing. Dialysis tubing has these tiny little holes in it, and so if I were to trace it out, we've got dialysis tubing here, kind of tied it in a knot at the bottom, and so it goes all the way up here. And then as we move up, the dialysis tubing is empty up here, but it's tied all the way up to a big ring stand at the top. So the dialysis tubing is filled down here. Now what's it filled with? It's filled with corn syrup here. And so that corn syrup is going to have a high concentration of solute. In this case, it's going to be sucrose or sugar. Outside of that, right out here, we have water. We have distilled water. And so if we look at these two in relation to each other, which of the following is hypertonic and which of the following is hypotonic? Well, the hypertonic is going to be the area with more sugar or more solute. And so in this case, that's going to be the corn syrup. And so we should have a flow of water in that direction. And so I'm going to turn on the video and then speed it up a little bit and so you can watch it and so you can see the magic of osmosis.
And so you can tell that this person is a high school teacher because there was several changes of classes during, if you watch the background of that video, I've watched this video enough times that that's what I do. And so you can see that in this experiment, when he started the experiment, the corn syrup, which has been dyed a different color, was right here at the water level, okay? And then over a time period, which I'm guessing is about 3 hours based on the number of classes that came through, but whatever time period he chose, that the corn syrup actually grew up out of this, and so anti-gravity grew up this because water was entering it, and so there was a greater volume inside the dialysis bag, okay? And now what we're actually going to be looking at, because we're talking about colligative properties, is osmotic pressure, which is symbolized by pi. And so it's basically the fact that it's the pressure applied when a solution just to stop osmosis. And so this is a screenshot, screenshot from the video, and I drew in here the fact that the difference in height from here to the water level would be equal to pi. If you go back to chapter 5, we did that with mercury. We would measure mercury and say J tubes or U tubes, and that's where the millimeters of mercury comes from. And so the formula is pi is equal to molarity, R, and since we're dealing with pressures of gas, it's the 0.0821, and temperature in Kelvin. Now I'm going to show you, the next slide we're actually going to do is a problem, but I want to show you an alternate form of this formula here. So first of all, pi is a pressure, so we can also symbolize it by being P, and molarity is the moles per unit volume. So basically I would have pressure is moles over volume times R times T. And so if I multiply both sides by the volume, I have pressure volume is equal to moles RT. And from chapter 5, this is the ideal gas law. And so you can use either set of formulas, and when I do the problem, I'm going to do it both ways, and you can choose which one you want to use. There's benefits of this one is given on the formula sheet. This one's not given because it's previous semester, so you'd have to remember it. But I do believe that the ideal gas law is the easier way of doing things, okay? And so they're basically the same formula, just rewritten in using different variables there. Now, before we go to the next slide, there's important uses to osmotic pressure. One is to determine the molar mass or molecular weight of large molecules, things like the corn syrup, or more importantly, it's usually used to determine the molar mass or molecular weight of proteins and biological stuff like that. Of course, I mentioned when I started this video the fact that in biology you study it a lot because it's used in cell membranes to transfer water across cell membranes. And then something you may not be familiar with is something called reverse osmosis. Reverse osmosis is meaning the fact that I'm actually going to apply pressure and force water out of the thing of higher concentration to the thing of lower concentrations. And so it's used to purify salt water. So if I have salt water of course has all kinds of things in it, mostly salt, sodium chloride, sodium bromide, but it has other things that we don't really want to mention about what's in seawater. And so a lot of coastal cities will use this in order to get their drinking water. In Georgia, we tend to use either one or two sources. Macon uses the Amogi River, which flows in downtown Macon. Peach County, Houston County, Crawford County all use well systems, which means that they've dug wells down and they're using underwater streams, basically. So we don't see reverse osmosis to purify clear water here or drinking water here, but it is, like I said, used in the big cities like Boston, San Francisco, things that live on, or cities that are near the ocean. And so in the next video, I will be doing a problem to show you colligative property.